So basically, the term or the by terminology electrodynamics can consist of two parts. Basically, it deals with electricity and magnetism. Okay, and their interaction also. Electricity and magnetism and their interaction. So electrodynamics deals with the electricity and magnetism and their mutual interaction. And electricity, this can be also classified in two parts. Whenever the charge is at rest, which is namely electrostatics, okay, and whenever the charge is in motion, so this is called the current electricity. So electrodynamics consists of these topics, mainly electricity and magnetism. And within electricity, you have two parts of this topic, which is one is electrostatics, the interaction between static charges, and the second one, current electricity. So we have started the study of such topics, suppose namely from electrostatics. In electrostatics, the interaction between two charges is described by the very familiar law, which is Coulomb's law. Coulomb's law. And you know the form of Coulomb's law. The electrostatic force between two charges is 1 by 4 pi epsilon naught Q1 Q2 by R square. And the corresponding electric field, or you can say electrostatic field of a point charge Es is equal to, suppose due to Q charge, so 4 pi epsilon naught R square R cube. So this is the electrostatic field, and which is conservative field, because curl of Es is equal to 0. So this is electrostatic field. Okay. And then you have magnetism. In magnetism, we have studied Biot-Savart law. Biot-Savart law. And Biot-Savart law dictates that a current carrying element, that means a moving charge, can produce some magnetic field. And the amount of magnetic field can be measured or can be determined following the Biot-Savart law, which has the mathematical form EB equal to mu naught by 4 pi I dl cross R by R. Okay. So these are the basic laws of electricity and magnetism. Okay, the basic laws of electricity and magnetism. But later we have found the interaction of electric field and magnetic field, and this interaction is mainly described in Faraday law. And later it is modified by Lenz, so you can say Faraday or Lenz law. Which dictates that there is an interaction between electric field and magnetic field. Okay. So electrostatic field will be conservative field. The curl of the electrostatic field is 0. It is irrotational. But in general, if a charge is moving, then the corresponding electric field will not be conserved. It it will not be quite conservative. So a moving electric field can produce a magnetic field. So there may be some interaction between electric field and magnetic field. So assembling all these things, you can construct the laws of electrodynamics. Okay? And all these things are assembled by Maxwell. So the basic laws of electrodynamics are known as Maxwell equations. Maxwell's equations. The basic laws of electrodynamics, the basic laws of electrodynamics are known as the Maxwell's equations. So there are four Maxwell equations. First, divergence of E is equal to minus rho by epsilon, and this law is known as famous Gauss's law, which is nothing but a form of Coulomb's law. So this equation comes from the electrostatic case, electrostatic interaction. Second one is divergence of B is equal to 0. That means the magnetic flux will always be 0. So the amount of north pole and amount of south pole will be same. So there will be the inexistence of magnetic monopole or distinct monopole. Okay, so magnetic interaction starts from the dipole term. So this is not the nomenclature equation. This dictates the inexistence of magnetic monopole. Okay. Number 3, which is very interesting, this is Faraday or Lentz's law, and in the form of vector algebra, you can write this is curl of E. Curl of E is equal to minus of del B by del T. Curl of E is equal to minus of del B by del T. Now, for electrostatic case, if we write the electrostatic equation, so if we write the electrostatic case equation for comparison, for electrostatic field, it was curl of ES equals to 0. Okay. Electrostatic field was conservative field, but in general electric field is not conservative. So that's why you have a non-zero term, and this is the time derivative of magnetic field. And the last one is Maxwell modified Ampere circuit, which is curl of B equal to mu naught. The modified Ampere circuit. So these four equations are together known as the Maxwell equations, and these are the pillars of electrodynamics. Okay. So these are the equations describing the dynamics of the electricity and magnetism, and this topic is known as the electrodynamics. Okay. So in arbitrary case, you can say that this rho and J are the sources of electrodynamics. Rho is the volume charge density, so these are one type of source, and J is current density, so this is also a source. So rho and J, rho and J, the source terms in electrodynamic interactions. So in arbitrary case, you can express these equations in a very arbitrary way. So I am quickly writing those equations, which is divergence of E each function of R in general, but in arbitrary case I am writing R of T equal to minus rho of RT by epsilon. Okay, sorry, this was not minus. Divergence of E was actually plus rho by epsilon. Sorry, I have made that correction. And then divergence of P of RT is equal to 0. Number 3, curl of E if function of RT equal to minus, and the last one, curl of B if function of RT is equal to mu naught J function of RT plus epsilon function of each function of RT. Okay. So in arbitrary situation, I am writing all these things may be the function of space as well as time, because the source is taken in arbitrary case. The source may be time varying. Okay, source may vary with time. So in that case, the electric field and magnetic field both may vary with time. So this form of the Maxwell equations just express the arbitrariness of these equations. These equations are applicable in every arbitrary situation, whether the source is static, whether the source is dynamic or accelerating, whatever it may be. These four equations are applicable in all cases, in all situations. Okay. Now look at here. What are the number of equations in this case? Okay. Explicitly, you can say there are four number of equations, but if you look at carefully, the last two equations are vector equations, right? The vector equations. So that means this equation, each of these equation contains three equations. That means x component of curl of E is equal to x component of that. Y component of curl of E uh, is equal to y component of that. So any vector equation is the assemble of three scalar equations. So these two are actually six equations. So 3 and 3, 6 plus 2. So there are 8 number of equations. 8 equations. Okay. And what are the number of unknowns? What are the number of unknowns? Hello. Please respond. What are the number of unknowns?
2.
6 number of unknowns. Ex, Ey, Ez, Ex, Ey, Ez. 6 unknowns. Okay, rho and J are given. These are the source term. You know the form of the source terms, rho and J. The unknown terms are the components of field E and B. So this is very interesting because 6 number of unknowns can be determined or have to be determined from 8 equations. So there are 2 extra equations here. So surely the 8 equations are not mutually independent. The mutually independent number of equation is 6. So there must be 2 interconnecting relations, and the 2 interconnecting relations are namely continuity equation, divergence of J plus del rho by del T equals to 0. So this is the first interacting or interconnecting equation, and also equation which is obvious, so that's why this is not written, which is the magnetic current density, divergence of Jm plus del rho m by del t equals to 0. So these two are the interconnecting equations. That's why you have only 6 independent equations. 8 equations are explicitly, but in independence, as per their independence, there are 6 independent equations. Amongst them, this is known as the continuity equation, and this is obvious because Jm and rho m, they are already absent in the equation. So these are constant, you can say. So this is 0. So this is the primary introduction of the basic laws of electrodynamics, namely the Maxwell equation. Okay. Okay. Now there are 4 explicit equations. You have already answered 4 explicit Maxwell equations. Amongst them, uh, the first and third, sorry, amongst them the second and third equation. These are somehow different from the other two. Second equation was divergence of B equals to 0, and third one was curl E equal to minus del B by del T. These two equations are independent of source. Independent of source. And other two are dependent on source. Okay, these two are independent. And from vector algebra, you can say that if you have any vector with divergence free, that means divergence of B is equal to 0, you can say that B will be the curl of any vector A, say. Okay, B can be expressed as the curl of another vector because as per the identity of vector algebra, divergence of curl of any vector is 0. So that's why B is equal to curl. Okay, this A is called the vector potential. Vector potential. Many may say that A can be called as the magnetic vector potential because this is the outcome of magnetic field B. But for your kind information, B is not A is not related to B only. Okay, A will also be related to E. In the expression of E, you will find A. So A is not only the vector potential, only vector potential, not the magnetic vector. So be careful while addressing this one. A is কোনটা?
ওই বি ইকুয়াল টু কার্ল অফ এটার ভেক্টর পোটেনশিয়াল ব্যাপারটা নিয়ে করলাম।
Okay, okay. So you have the equation divergence of B is equal to 0, and as per the identity of vector algebra, divergence of curl of any vector is 0. So you can say that B must be the curl of other vector, and this vector I am taking as A. So B is equal to curl, and this A is a vector quantity. That's why it is called vector potential. Okay. But in some books, it is claimed that A can be named as magnetic vector potential because it uh, comes from the magnetic field B. But it is not only related to magnetic field B. It will also be related to E. So that's why it is not magnetic vector potential. It is only vector potential. Okay, it is only vector. So similarly, from this equation, from this equation, curl of E is equal to minus del del T of curl A. Okay, this is curl A. Okay, now curl of plus del A by del T is equal to 0, right? From this equation, you can express this equation in that way. Curl of all these things, E plus del A by del T is equal to 0. Okay. And from vector algebra, you know, curl of gradient of any scalar is 0. So from this idea, you can write E plus del A by del T will be the gradient of some scalar phi. Okay. And actually, from convention, we have to write this is minus of grad phi. And this minus convention comes from the electrostatic case. In electrostatic case, we have already studied that ES is equal to minus of grad phi s. Okay. So ES was electrostatic field. So by analogy, here also it is not the electrostatic case. That's why you have del A by del T also. So E plus del A by del T, this is minus of grad phi, and this phi is electric scalar potential, because phi is only related to E. Okay, in the expression of E there is no phi, so it is electric scalar potential, and so that's why E is equal to minus of grad phi minus of del A by del. Okay, so from the second and third Maxwell equation, you can express the fields, okay, the unknowns of Maxwell equation E and B in terms of some potentials, namely electric scalar potential phi and the magnetic. I am also making the mistakes, and the vector potential. Okay, these are the potentials of field. Okay. So these are the outcomes of fields. So these are the Maxwell equations. Now you have these potentials. And in terms of potentials, okay, in terms of potentials, you can write or you can express the four Maxwell equations in terms of this potential. But there are some problems for expressing the Maxwell equation in terms of I and A. Okay. There may be some issues, and you have to resolve these issues by further study. Okay. So, what are the problems or issues in expressing the Maxwell equation in terms of potential I and A? So, we have to look at these issues first, and after that, we are going to resolve these issues. So, at first, we are trying to express the Maxwell equations in contravariant form. In contravariant form of Maxwell equations, ME. So here we have the source term rho, rho and J, and this is written as J mu for current density. That means the zero component of J is rho. Okay. And the potentials I and A, this is suppose A mu, this is called EM for potential. Okay. So in terms of this potential terms, terms of these potential terms, you can express the Maxwell equation. And the Maxwell equation can be written that way: del mu m mu nu equal to z nu, the contravariant form of Maxwell equation. And m mu nu equal to del mu a nu minus del nu a mu. And this m mu nu is known as m field tensor. Okay. So you can put the value of m mu nu here. So this is del mu a nu minus del nu a mu equal to 0. Okay. So this is the contravariant form of Maxwell equations. The four Maxwell equations can be written in one contravariant form. This one. Okay. Now try to solve this Maxwell equations in contravariant way. So here, this is a partial differential equation, right? This is PDE. And in order to solve PDE, at first you have to express each and every term of this equation in terms of the Fourier transform. Okay. So in terms of the Fourier transformation, suppose this a mu will be the function of the space-time 4 coordinate x mu will be equal to 1 by twice pi whole square. This is integration of 4 volume, and this will be, suppose, a mu tilde function of k nu e to the power I x mu k mu of d k mu. Sorry. Okay. So this is the Fourier transformation a mu. A mu tilde is the Fourier transformation of a mu and vice versa. Similarly, suppose the Fourier transform of j mu, which is function of x mu, is suppose j mu tilde is function of a. So transformation from x mu to k mu, this is Fourier transformation. Now if you put this Fourier transformation in the equation, you have the derivative with x mu. Okay, derivative with x mu of these things. So after derivative, I will find I k mu covariant and I k mu contravariant. So this is the minus. So look at carefully. It will be minus k mu minus k mu and then a nu tilde. Okay. And then you have minus and minus plus k mu and k mu and k nu of a mu tilde equal to j nu tilde. So after making the Fourier transformation at the both sides, you will find this form of equation. So k mu is the tensor product, tensor inner product, which is k square. So you have k square. So I am taking minus k square to be common. So a mu tilde minus of a mu by k square of a mu tilde is equal to minus of j nu by this
বিকালের
okay,
সময় তো ক্যাম্পিং ছিল,
this one.
ক্যাম্পিং সবসময় থাকে।
And the right hand side, suppose
মাংস
this a new tilde,
মাংস 10 টাকা,
a new tilde you can write
রোববার
as
দিন
uh,
মাংস মাংস থাকে।
chronica delta
আমি
mu nu
যে যা যে কিনবে কিনবে
of
না,
a new tilde.
আমিও মাঝে মাঝে কিনে খেতাম
Okay,
মাংস,
a mu
মাংস
tilde,
ভালো
a
লাগে।
new tilde is equal to
ঠিক আছে,
sorry,
বেশ মজা লাগতো। তারপর শুক্রবার দিন মাংস কাবুল, মাংস ঘুগনি,
a new tilde
শুক্রবার দিন
is
খাই।
equal to
সেটা কাউকে
chronica
বলবো না,
delta
সেটা
mu
খাবো।
nu of
বুঝতে পারছি,
a
যতটা
mu
মনে আছে
tilde.
আমি ঠিকই বলছি।
This is
মাংস
equal to
ঘুগনি,
a new tilde.
মাংস ছোটো ছোটো ঘুগনি, ছোটো ছোটো মাংস
Okay,
ঘুগনির সঙ্গে ওই কাবুল, ওটা
so
ইয়ে হতে পারে বা ইয়ে, আমার ওটা ভুলে যাচ্ছি,
if you
ওটা
put
মোটা
this
হতে
one
পারে বা কাবুল ছড়া
here
হতে পারে, বুঝতে পারছি
in
ব্যাপারটা।
the place of a new tilde, you will find chronica
মাছটা
delta mu nu
আমার এসছে রেস্টুরেন্টের খাওয়ার মতো,
minus k mu k nu by
ফাইনাল
k
মাছটা যেটা
square
হতো না, হ্যাঁ
of
ফাইনাল তোমার ডেটা বইতে
a
একদম
mu
ফাইনাল
tilde
বা
is
সাউথ
equal to
কোরিয়ান,
minus j nu tilde by k
দারুণ
square. Okay,
সকালবেলা
is it okay? Or you have any question?
এমনি মাঠে
You
মাছ
can ask any
ধরা,
type of question from here.
তারপর ইয়ে,
স্যার পেজটা
তারপর শুন,
Okay.
শুনলি, তারপরে তো ওই যে প্রতিদিন তো খাওয়াটাও ভালো হতো। তারপর সামনে জানিস তো খেলা হতো, ক্রিকেট খেলা হতো,
This one we
ক্রিকেট
have
খেলা
started
হতো যে গ্রাউন্ড ছিল,
from the original form of
মজা হতো।
Maxwell equation. This one. Now express the potentials in terms of their consecutive Fourier transformation. Then put this one.
ব্যাকগ্রাউন্ড তো
So
পাওয়ার বেশি না,
derivative with x mu.
হালকা মাসে
Okay, I k mu and I k mu
কত
correspondingly
অর্ধেক
it will I
মাসের জন্য
minus I
একবার
and I minus one.
ওই
K mu and here minus and already there was a minus, so
মোটামুটি
minus and
মোটামুটি
minus
সাড়ে
plus k mu of that one.
মানে সাড়ে
After
চারটে
this
ছিল,
very
যার
simplest
বেশি
calculation.
বেশি হয়েছে বলতে মেয়েরা দুটো নাকি
Okay,
বেশি হয়েছে,
on this one.
সেটাও হচ্ছে না, মানে যাদের
Okay,
যে কেউ তো 5,000 টাকা দিয়ে রাখতে পারবে না, সে নিশ্চয়ই বড় লোক বা কিছু কাজ
okay.
টাজ করে,
Or any question?
মোটামুটি আছে বলে রাখছি, সেইটা বলছি। নিশ্চয়ই সেই সেই হ্যাঁ,
Hello.
অবশ্যই আছে। যে ধরো ইয়ে করছে, যে ধরো ফুচকা চালাচ্ছে, সে কি 5,000 টাকা দিয়ে রাখতে
Okay,
পারবে?
I think it is okay.
কিন্তু যে সরকারি স্কুলে চাকরি করে বা
So now,
বিজনেস করে বা ইয়ে করে, দোকান টোকান, বড়
so
বড় চায়ের
this
দোকান, মানে
all of
হোটেল
these
টোটেল আছে,
things like a operator equation.
এই হচ্ছে
The left hand side
আর হোস্টেলে
contains some
ম্যাথ
operator
স্কুলটা মানে ছিল,
operated over a nu and it will yield some right hand side.
প্রতিটা ফ্লোরে
So
ইয়ে
this equation
সাড়ে 9:30
I am
করে
writing suppose p mu nu. Okay, this is
এই। তারপর
e mu nu
তবে একটা জিনিস কি
over
বলতো, তবে গার্ডিয়ানকে না ঢুকতে
a
দেবে
mu
না
tilde is equal to minus
বাইরে, বাইরে
j nu
ঘরের
tilde
সামনে আসতে দেবে না,
by
প্রতি
k
শনিবার
square.
রবিবার দিকে আসবে, সেরকম সিস্টেম নেই, বুঝতে পারছি তো, সেরকম
So now this
খাওয়ানো
p mu is equal to chronica delta mu nu
দেখা করতে
minus
দেখা করতে দিবে না,
k nu
নিয়ম নেই দেখা, তবু যে
by k
ইচ্ছা তাকে
square.
ঢুকে, কিন্তু
Okay,
অ্যাকচুয়ালি ওই রোববার দিন,
so
রোববার
we
দিন
can
যখন
show that this
রবিবার
operator is a
বাইরে
projection
ডিউটি,
operator
সপ্তাহে যদি
or
ছুটি থাকে,
idempotent operator.
অফিসে থাকবে, অফিসে
We
কি
can show that this p mu nu
ওরা এরকম কিছু কিছু তুই তো
is
বলছি, তারপর শুন, তারপরে তুই যে রোববার দিন যে
idempotent
ইয়ে না,
operator
তুই যে ধরো একটা
or
অসুস্থ আছিস, তুই যে
projection.
রোববার দিন যাবি না, অসুস্থর কথাটা কইতে পারছি না, অসুস্থ
Idempotent operator is such that
কি একসঙ্গে থাকে,
s
ওইরকমই আছে,
square equals to a equals to a cube equals to a to the power n.
বাইরের নিয়মের মতো করছে,
So such type of operator is called that means a square equals to a. This criteria is sufficient to define the idempotent operator.
সত্যি কথা
And you have suppose already
আমাকে
studied the
এই
projection operator.
প্রথম
Suppose p
দিন
alpha. P alpha is
আমরা
equal to
ভর্তি
alpha,
হতে অনেক
right?
পূর্বেই আছি,
Now suppose p square
একটা
alpha.
জায়গায় পড়তাম তো, বড়
It
বড়
will be
ক্লাস,
alpha alpha
প্রচুর এক্সটেনশন থাকতো,
alpha
এটা থাকতো,
alpha. So this is one. Okay. This alpha alpha. This is equal to p alpha. So p square equals to p. So projection operator, it is also an idempotent.
একটু হিন্দিতে বলতো,
Okay.
ওই সাল বছর,
So what is an idempotent operator? So any power of any operator will
না
will repeat the same thing. So a square equals to a, a cube equals to a to the power n equals to a. That means a is an idempotent. So here this p mu nu, you can show that p mu nu is also an idempotent operator. Okay. So suppose p square of mu nu. Okay. So p square of mu nu means p mu alpha and p alpha nu. Because alpha and alpha will contract and it will yield p square. Okay. So what is p mu alpha? Which is conical delta mu alpha minus k mu k alpha by k square. And p alpha nu is equal to conical delta alpha nu minus k alpha k nu by k square. Okay. Now make the multiplication. Conical delta mu alpha and conical delta alpha nu, alpha alpha will contract, and after contraction you have conical delta mu nu. Then conical delta with this term. There was a alpha at the contravariant rank and here is covariant rank. This will contract. So you have k mu, sorry, minus k mu k nu by k square. After that you have this term. This is also same. This is k mu k nu by k square, and then plus k mu and then k alpha k alpha. K alpha will be k square k mu by k to the power 4, which is k square. So one term can be cancelled. So you have conical delta mu nu minus k mu by alpha square, which is again p mu nu. So
স্যার
p square of okay.
স্যার আগের পেজটা
Hello.
হ্যাঁ স্যার এখানে যে থার্ড টার্মটা আমরা যখন মানে ডেল্টা অফ মিউ আলফা যেটাকে ওটাকে যখন মানে ফার্স্ট যেটা মিউ আলফা ডেল্টা ওটাকে যখন ফোর্থ টার্মটার সাথে গুণ করছি তখন ওই আলফা আলফা কন্ট্রাডিক্ট হয়ে গেল,
এই আলফা এন্ড আলফা
হ্যাঁ কন্ট্রাডিক্ট হয়ে গিয়ে কেমিউ হয়ে গেল। কিন্তু যখন স্যার আমরা সেকেন্ড টার্মটা থার্ড টার্মটা গুণ করছি তখন যে ডেল্টা অফ আলফা
সেকেন্ড এন্ড থার্ড ইজ দিস টার্ম এন্ড দিস টার্ম,
হ্যাঁ হ্যাঁ হ্যাঁ
this one and this one,
তখন তো স্যার
the same thing.
আমরা তো
Alpha and alpha will contract. Alpha, okay, same thing. Alpha and alpha will contract, then you will yield k nu. K mu was there and again a k nu. Alpha will contract. So k mu by k square. Okay. K alpha nu. This is k nu. Okay. So that's why k mu by k square. Okay, so similarly, if you can find the p cube mu nu, this will same the p mu. Okay, so the Maxwell equations at last can be expressed as an operator equation having an idempotent operator p mu nu of a mu tilde is equal to minus j nu tilde by k square. Okay, this p mu nu is an idempotent operator, and such equation where at the left hand side there exists an idempotent operator, these equations or this type of equations cannot have the unique solutions. So these equations cannot uniquely solvable. Okay,
স্যার কেন ইউনিক
these equations cannot be uniquely solved because the eigenvalues of p square and p cube and p to the power n is same. So that's why the solutions cannot be made unique. Okay. In mathematical physics, you have already studied these ones for eigenvalue equations. Whenever the operators are idempotent or projection operator, in such cases you cannot find the unique solution for for such equation. So the message is clear. Maxwell equations cannot be uniquely solved. Maxwell's equations cannot be uniquely solvable. So the attempt is very fatuous. Okay. The attempt is not required to solve the Maxwell equation because these are not uniquely solvable. Okay. But you know the continuity equation. The continuity equation is divergence of j plus del rho by del t equals to 0. And in contravariant form, you can write del mu j mu equals to 0. Okay. So now take the derivative with respect to j nu at the board equation, and that means you have del nu p mu nu of mu tilde of minus del nu j nu tilde by k square. As del nu j nu is 0, so this is 0. Okay. So del nu of p mu nu mu tilde is equal to 0. So as p mu nu derivative of this thing is 0, so you can say p mu nu of mu tilde, which is constant. So mu tilde is not unique, but the projection of mu tilde, this is unique. This is very interesting. Okay. So it is fatuous to find mu tilde, but still the projection of mu tilde along any particular direction, this is constant. So you can try for these ones. You can solve for these one. Okay. But in terms of the potentials, the Maxwell equations cannot be found in the solution of the Maxwell equations cannot be found uniquely. Okay. And geometrically, you can express this thing. Suppose you have already found the solutions of Maxwell equation are not unique. So these are the set of solutions. These are the set of solutions. Mu tilde, which is not unique. Okay. But the projection of this, the projection of mu, the projection of this mu will be same. So geometrically, the projection is that. This is the projection. So these are the set of mu, but the projection is one. This projection. This is p mu nu mu tilde. Okay, so mu tilde is not unique. There may be infinite number of possible choice along these lines, but the projection will be identical. Projection is unique. It's projection. So this is the geometrical scenario regarding the solutions of Maxwell equations. Okay. So however, we have found that the Maxwell equations cannot be solved uniquely. Okay, there will not be any unique solution for Maxwell equations. So in this case, we may find some good choices of solutions. Okay. We may take some good choices of solutions. Okay. As there is no unique solution, there may be different kind of in fact infinite number of possible solutions for a mu. So this is the set of solutions of a mu, and amongst them we can take some good choices of solution. Some good choices of solution. Such good choices of solution is called
স্যার কনসেন্ট্রেট করে খুব মুশকিল হয়ে গেল আমি দেখছি হ্যাঁ আরে কী বলবো
gauge solution.
মুশকিল হয়েছে হবে আস্তে আস্তে করতে হবে
Okay.
টেনশন নেই
So
হাজার
the summary is that
দেখি
Maxwell equations are not uniquely solvable.
প্রচুর
There may be a set of solutions.
কতটা চঞ্চল
Amongst them, you can take some good choices of solutions which are physically suitable. Okay. So such solutions are known as the gauge solution. Okay. And in our known electrodynamics, in our familiar electrodynamics, there are two popular choices of good solutions. And these good choices of solutions are namely,
40 মিনিট বাকি
first is Coulomb gauge
ঠিক আছে করতে
and second is Lorentz gauge. So these are some particular choices of Maxwell solution. Okay. So we have to study for this Coulomb gauge and Lorentz gauge. Suppose you have a particular Lagrangian with Lagrange's equation of motion d by dt of del L by del Q k dot minus del L by del Q k equals to 0. Then another form of Lagrangian L prime is equal to L f by dt is also satisfying the same Lagrange's equation of motion. So Lagrangian is also not unique for a particular equation. L, the solution for L is not unique. Okay. So you can take some good choices of Lagrangian. Okay, and you can take those choices by choosing this function f, and this f is called Lagrangian gauge. Lagrangian gauge function or gauge. Okay. So here also we have two popular choices of good solutions for Maxwell equation. Now come back to the vector or scalar equation from the contravariant form of equation. So the second equation, divergence of E equals to 0. And from here you have B equal to curl A. Okay. So suppose you have a primary choice for the solution of A is A naught. Okay, A naught is some particular choice of A. So that's why it will satisfy the equation curl of A naught is equal to B, right? Then also A equals to A naught plus grad lambda. This will also satisfying the same B or same equation or same Maxwell equation. Okay, because you know curl of gradient of any scalar is 0. Okay, so if you have any particular solution A naught, then also the solution A equals to A naught plus grad lambda will satisfy the same magnetic field. Okay. So A naught is not unique. You can take other form of A by varying the value of lambda. So this is lambda, which is gauge function. Okay. Similarly, from the third Maxwell equation, curl E equals to minus del B by del T. Okay. So here E equals to minus of grad phi minus del A by del T. And here if you choose the primary solution to be A naught and phi naught, then also A equals to A naught plus grad lambda and phi equals to phi naught minus del lambda by del t will satisfy the same E. You can put that. If you put these values, this will same the same E. So lambda is the gauge function. If you have some solution A naught and phi naught, then you can construct the other functions, other solutions by this lambda without affecting the physics. Okay. So here lambda is gauge function. Okay. Now what is Coulomb gauge? Coulomb gauge. Coulomb gauge is such a choice of A so that the divergence of A will be zero. Okay. So Coulomb gauge is such a choice of A. Okay. There is no restriction on A to be conservative or to be conserved. A may not be conserved, but if you take some Coulomb gauge solution, Coulomb gauge will restrict the solution to be conserved. That means divergence of A will be zero. So here you have divergence of A naught plus grad lambda. This is to be zero, and grad square lambda is equal to minus of divergence. And after solving this equation, you can find the lambda. And if you put this lambda, then you will find the Coulomb gauge solution. Okay. And from Coulomb gauge solution, suppose you have the final equation, Ampere's circuital law. This is curl of B is equal to mu naught J. Mu naught J plus epsilon naught del E by del. Okay. Now this is curl A is equal to mu naught J plus mu naught epsilon naught del T of minus grad phi minus del A by del. Okay. Okay. Now this is Coulomb gauge. In a Coulomb gauge, divergence of A equals to zero. Okay. And another popular gauge is Lorentz gauge. In Lorentz gauge solution, the restriction on the solution will be divergence of A plus 1 by c square del phi by del t equals to 0. So this is the restriction on the Lorentz gauge. So if you may have infinite number of solutions, but the Lorentz gauge solution will be those solutions which will satisfy this equation. Okay. So from here you have this is grad of divergence of A minus of grad square A, okay, equals to mu naught J, and mu naught epsilon naught is equal to 1 by c square. So 1 by c square minus minus 1 by c square grad of del phi by del t and minus del 2a by del t. Okay. So from Lorentz gauge, you have divergence of A plus 1 by c square of del phi by del t equals to 0. So those two things will yield 0. So then you have grad square A minus 1 by c square del 2A by del T2 equals to minus mu naught Z. Okay. Similarly, I am leaving some homework for you. Suppose I want to express the Maxwell first equation, the Gauss's law. Divergence of E equals to rho by epsilon. Now you have to this Gauss's law, express this Gauss's law in terms of A and phi. Okay, and following the Lorentz gauge solution, Coulomb and Lorentz gauge solution. Okay, and this will be homework for you, and surely you will find this one, that grad square of I minus 1 by c square del 2 phi by del t2 equals to rho by epsilon. Okay, so that means you have grad square minus 1 by c square del 2 del t2 of phi equals to rho by epsilon naught, and grad square minus 1 by c square del 2 del t2 of A equals to minus mu naught Z. So these two are the governing equations from Maxwell equations, and this has to be solved. This has to be solved. Okay. So these are the D'Alembert operator. So grad square of box square of phi is equal to rho by epsilon naught, and box square of A, this is minus mu naught J. And these are the inhomogeneous wave equation. You know the normal wave equation, homogeneous wave equation. Grad square psi equal to 1 by c square del 2 psi by del t. This is homogeneous wave equation. But the Coulomb gauge and Lorentz gauge solution of Maxwell equation is satisfying the inhomogeneous wave equation. Grad square phi is equal to that, and grad square A is equal. So from here, you have to solve this one, and after solving this equation, you can find the effect of electrodynamics or study the nature of electrodynamics in terms of the potential. Okay. So in the next class, we shall discuss how to solve this equation. And behind solving this equation, you have to follow some crucial mathematical rules or mathematical tools to solve this inhomogeneous differential equation. And these mathematical rules are mainly based on the green function technique. Green function. Okay. And this green function technique is mainly included in the syllabus of universities. Okay. Specifically, one or two universities will emphasize on the green function technique. So the main intuitions or main purpose of learning this green function technique is to solve the important physical equations which may find while studying the laws of physics, mainly in electrodynamics. Because in electrodynamics, you have to solve more and more of these inhomogeneous differential equations. And in order to solve this differential equation, you have to study the green function. So in the next class, and also we have to study the green function technique and apply the green function technique to find the solutions of Maxwell equations. Okay, and also the other aspects like linear Ricard potential, time retarded and time advanced potential. All of these things will be discussed in the next subsequent classes.